Okay, we are today, lost my stylus. This could be bad since I write with it. I don't suppose anybody's seen my stylus on the floor? There it is. Okay. Man, had me worried there. Oh yes, I didn't take record yet. Michael, Chad, no, he left. Bridget, yes. Ann, yes. Reagan, not yet. Lindsay, yes. Helena, yes. Diksha, yes. Austin, yes. Zach, yes. Sally's back. I'm going to count you on time. No Cassie. Michaela. Tucson. Tori. And shut it. Okay, so the ones I don't see are Chad, Reagan, and Cassie. And of course, I just set my stylus back down the same place I couldn't find it. Okay, today we're going to be looking at particle physics, the last section we're actually going to cover. And we're going to start with a clicker question here. So the question is, what does the root word for atom, which is atomos, mean in Greek? Okay, we had more spread than I thought. Atom meant indivisible. That was the idea of Democritus, that if I cut something into pieces, I'll get smaller and smaller pieces until finally I get to the point where it's no longer divisible. He called this an atom, meaning I got to the indivisible piece. Well, as we've gone through looking at matter, we've realized that it's a little more complicated. So here's a breakdown of what we currently understand for matter. We have solid things, like this table. But those solid things can be broken down into molecules. Molecules are atoms that are held together by bonds formed because of quantum mechanics, the energy levels of electrons. But then those atoms themselves have electrons orbiting a nucleus, the nucleus containing protons and neutrons. And then we're going further than that in this chapter. So, what is a nucleon created of? Well, as we will learn, our current understanding is that there are 3 quarks. Well, what's a quark? It's a really good question. But those quarks themselves are held together by these little tiny things called gluons. So we have quite a range in the particles that we call subatomic particles, particles that are smaller than the atom. And so we're going to learn as much as we can about those today. And hopefully somewhere along the way we'll get an inkling of why scientists spend time and energy on this. So first, a very interesting understanding that developed in the beginning of the 20th century, that particles mediate forces. Now, I can illustrate this with a simple demonstration. Chad.
Yes.
I'm going to throw this ball to you, okay? You're going to catch it, right? So I throw it. When I throw it, I'm going to put a force on the ball. Agreed? Now I throw it. When Chad caught it, what did the ball do to Chad? It applied a force on Chad. Now this force, if we were on ice and I had no friction, when I threw it away from me, what would I have done in response to that force? I would have moved away. Would Chad have moved away the instant I threw it? No. When would he have moved away? When he caught it, because it would transfer momentum to him. So that's the idea of a particle mediating a force. But it gets a little more complicated, sadly. the particles mediating the forces are virtual particles. And when I say a virtual particle, I'm sure that conjures up all kinds of crazy ideas. Here's what it means to say it's a virtual particle. A virtual particle is a particle that we cannot measure and that is violating conservation of energy. Does that make you feel good to know that we're talking about now particles that violate conservation of energy? No, it doesn't make me feel good either. But that's okay, because we've learned the Heisenberg uncertainty relation. And the Heisenberg uncertainty relation has an uncertainty relation that relates to energy. You may or may not remember it, so I'm just going to write it down. The uncertainty in energy multiplied by the uncertainty in time has to be greater than or equal to h over 4 pi, or if you like, that's h bar over 2. That was our uncertainty relation. And the physicist said, hey, it is no problem to violate conservation of energy as long as the amount of the violation, the delta E, multiplied by the time through which you're violating conservation of energy, delta T, is under that h bar over 2. And so they say, okay, so we can have violations of conservation of energy, but only for very short times. So these virtual particles, we can't measure them. They're not around very long. But they are going from one particle to another. Now, with my example between Chad and me, I don't know. I'm suddenly in conflict if it's me or I. And the ball. That was a repulsive force that we were mediating with the tennis ball. But between electric charges, we can have repulsive or attractive forces. The particle that mediates the electromagnetic force is the photon. The photon, but the photons we tend to think, okay, so it's always going to be like the tennis ball, making a repulsive force. But with these virtual ones, they can also be attractive. So the picture on the left is showing a force between two protons. One proton kicks off a photon, starts moving away. The other proton, when it receives the photon, it starts moving away. That's how the particle is mediating the force. That is a fundamental aspect of particle physics, that particles mediate forces. Now, the picture on the right is showing a photon that is intercepted by something like our eye. Well, then it's not going to affect another proton. We just see it. But it's the same type of thing. So, Hideki Yukawa, in 1931, he was studying this idea that particles mediate forces, and he said, okay, the electromagnetic force isn't the only force out there. There's also the strong nuclear force. And so he did some calculations based on the range of the strong nuclear force to calculate how much time you would have to have, how far apart the particles could be if you're still going to have a strong nuclear force, and thus how much time a particle could live to go from one nucleon to another. And it was, of course, a very short time. Using that uncertainty relation, it gave him a fairly large mass. A mass that was somewhere between the mass of an electron and the mass of a proton. So he called that mass a meson. Meso meaning in the middle. So he predicted this meson, and within a year, American Carl Anderson had discovered that pi meson. It must be on the next slide where I have the numbers. I'm pretty sure I put those numbers in. Oh wait, this is 1935. Maybe I'm thinking of the wrong people. Anyway, within a year, the pi meson. Oh yes, I am thinking about the wrong thing. It wasn't Carl Anderson. Different. They found this pi meson, as they called it, and that pi meson is now called a pion, and it is a particle that mediates the strong nuclear force between two atoms. Now, it turned out it wasn't what he really was looking for, so they had to go looking some more, and they have the gluon for the fundamental particle to mediate the strong nuclear force. But that was the first prediction made by this idea that then found a particle. And it's almost like finding Pluto. Right? They made a prediction of the planet Neptune, then they looked and they found it where it was predicted. And then they, based on the orbit of Neptune, they said that still ain't right. They made a prediction of another planet. They looked for it and they found Pluto. But then they quickly discovered Pluto didn't have the right properties. Pretty much the same thing here happened with the Yukawa particle. But it was a prediction, and then they found something. I was going to bring out this table and put it in the back of the classroom, but the truth is, my PowerPoint software kept crashing when I was making your lecture, and I had to redo the presentation a couple times. So I didn't have time to do it. This here is a nice table put out by the Contemporary Physics Education, I can't remember what the last P stands for, talking about what the fundamental particles are. And I want to start by zooming in here. We have 4 known forces: gravitational force, the weak force, the electromagnetic force, and the strong force. My finger is not touching it despite what you see up there. That circle means it thinks my finger is there right now. In those forces, we have strength drawn on here, or written on here, 2 different separations. 3 times 10 to the minus 18th meters and 3 times 10 to the minus 17 meters. Why the 2 different distances? Because the strengths vary with distance. And so you can see here which force is the strongest in all cases. Yeah, the strong has the biggest numbers in all cases for both numbers. Then which is the next strongest? Electromagnetic, then the weak, and finally gravitational. Look how weak gravitational force is at these short distances compared to the others. That's why we don't worry about gravitational force when we're talking about the energy levels of electrons orbiting nuclei, because the strength of the gravitational force is really weak compared to the others. Each one has its particles that mediate the forces. So the strong nuclear force is mediated by things that are called gluons, not the Yukawa particle, not the pi meson or pion, but by gluons. Electromagnetic force, what is the name of that symbol? Gamma. And this gamma is coming from the same gamma as gamma rays for radioactivity. That is photons. So photons are the particle that mediate the electromagnetic force. Then we have the weak interaction, which has W plus, W minus, and Z0. 3 particles that mediate the weak nuclear force. And then the gravitational force. And this has not been updated yet because it still says the graviton not yet observed. Since they've observed gravitational waves with the wave-particle duality, that means you've observed a graviton. So now they're starting to have some information about it. How much information, I think, is still real slim. But at least there is some observation there that it might exist. Now, these particles that mediate the forces are given a special name. They're called the gauge bosons. Gauge is not written here. It's just like you'd think it is gauge, and it actually means what you would think it means, almost. Gauge theory is a theory about you can put an offset in and it doesn't change things, kind of like potential energy. You can measure 0 potential energy at any reference point you choose. That's the essence of what gauge theory is about. You can set your references for energies. There are certain things that you can put into your quantum equations that don't change the outcome. And so it's called gauge theory, and hence these are the gauge bosons, so the bosons associated with gauge theory. But what the gauge bosons are the particles that mediate the forces. So here we have the summary once again of the particles, except for it has a little different information. The photon has a mass of 0. Photons have no mass. They are the only known particle with 0 mass. And of course, they have an electric charge of 0. If we look at the 3 particles that mediate the weak nuclear force, 2 of them have an electric charge. That's the first curveball to me. You know, when we talked about the ball example, there was no charge. This is the weak nuclear force. The weak nuclear force is independent of charge. And yet the particles that interact and mediate the force actually have 3 charge states: negative, 0 and positive. And so the names W minus, W plus, and Z, they're specific names that I don't know if we'll get to today. For the strong nuclear force, we have the gluon. This shows the gluon having a mass of 0. I'm pretty sure it's not 0. Remember I said the photon is the only known particle with a mass of 0? Yet this is made by people who know way more than me. So maybe there's a gap somewhere in my knowledge because it says 0 there, and electric charge of 0. The gluon looks a lot like the photon in the numbers here. And then finally there's that Higgs boson. The Higgs boson is I went through all the math of this last year. I couldn't explain it again. But it's really complicated math and getting to what the Higgs boson is. But it is generally described as the particle that's responsible for us feeling mass. Some other things, well, since I'm showing the particles here, let's go to elementary particles. Elementary particles are particles that cannot be broken down into smaller pieces. Now, oddly enough, elementary does not mean stable. You have things like the muon. The muon is like a heavy electron. If you look at the mass of the muon compared to the mass of the electron, that is approximately 200 times the mass of an electron. Otherwise, it's just like an electron. It has a negative charge like an electron, etc. But it's unstable. It will decay. It doesn't break into something smaller, but energetically, it will basically be destroyed and produce other particles that are more stable. So these things here, leptons, the word lept means light. So they're light particles. Why are they called light particles? Because the electron is light. They were named when the electron was the only known particle in the group. Right? Because if you take the tau particle, compare the tau particle to the mass of a, I'm trying to think of, what's the mass? The mass of a proton, I think, is about 0.97 or 0.98 gigaelectron volts per c squared. So the tau particle is about the mass of 2 protons. Generally, you would consider that light compared to a proton. But the electron is. So these things over here, the leptons, they have spin 1/2. Because they have spin 1/2, they're fermions, hence the title fermions. The leptons are a category with 3 negative particles, 1, 2, 3, and 3 neutral particles of much less mass, 1, 2, 3. And each one has an antiparticle. Now, I haven't gotten to Dirac with his antiparticle idea, so we'll get to the antiparticles later. So there are 6 items plus their antiparticles, so a total of 12 if you count the particles and the antiparticles. Then we have the quarks. We'll talk about Murray-Gell-Mann and the idea of the quark. And the quarks, there's 6 of them. There is a theory that says you should have the same number of quarks as leptons. Notice these are also spin 1/2. So they're fermions again. And we have those 6 things. Notice it says top and bottom. Top and bottom are the boring names. The less boring names are truth and beauty. They're interchangeable. You can call it the bottom quark, you can call it the beauty quark. Likewise, top quark or the truth quark. So we have these fundamental particles, once again 6 of them, plus their antiparticles. Notice the charges on these are not integers. I've talked about that before. But it turns out that energetically, it's not possible for you to have a bare quark, a quark that's all alone. They always come at least in 2s, and if they come in 2, it's going to be a quark-antiquark, and you always have integer charges when they come. So you never find them with these charges. So these are what we believe are the fundamental particles. We have these fermions over here, and then we have our gauge bosons, and the gauge bosons, these here are not fundamental. That is, those can be broken down to smaller things. whereas the others, the photon, the gluon, and the Higgs boson, those are fundamental things. So, yeah, there's a lot more on this. This is actually a super, super cool diagram with all kinds of information that any reasonable person would want to know, just because it makes them, well, it makes your mind go crazy. Okay, a question about all those particles. What is a gauge boson? This is not what I expected. I thought I spent a lot of time on the gauge bosons. Apparently not, because that's not what they are. Okay, the gauge bosons are the things up here in the top right-hand corner. Zoom in on them. These things here, I guess it doesn't say here, well, it says force carriers. Or if we come down to this chart here, it said the particles mediating the forces. Because that's what the gauge bosons are. They're particles that mediate the forces. That was the correct answer. I'm not going to worry about asking what the term gauge meant. What does boson mean? You have to think back to yesterday afternoon. Okay, yeah, it's like Subhandra Bose or something like that, and Einstein. Bose was the one who did the primary work. He's the one the name is. Those are particles that have spin of integers. Why did I talk about these yesterday? Because we had people talking about superconductivity. And in order to have superconductivity, we need our electrons to behave as bosons rather than fermions. But electrons have 1/2 integer spins. They're fermions. And so what was the solution to be able to have electrons act as bosons? Pair them up. You have what's called Cooper pairs of electrons bound together. And of course, any reasonable person says two negative charges are not going to be bound together by electrostatic force. They're going to be repelled. But it's a matrix force. It's forces from the other electrons and atoms that holds them together. It's not a bond between the two. It's they're being pushed together by other things. All right, back to non-zoomed. So, what was the correct answer here? I'm going to re-poll this. If we don't get this all right, I'm not going to stop the lecture. And I won't cry in public. Thank you for changing to the correct answer, Jaron, but we still had one person who didn't. Well, he changed to the correct answer. It's not calling him out.
Well, maybe you had the right one the first time.
What? Yes. Well, it's not really participating if you just put a default answer in without reading. Okay. Richard Feynman. As with all people named Richard, he was a genius. In fact, yeah, I'm glad you appreciate that. His official biography, not an autobiography, but his official biography is entitled Genius. He's considered the greatest mind of our generation. Our generation probably not being your generation. He was the youngest person to work on the Manhattan Project. He died when I was in college. He got a Nobel Prize for these things. Well, among others. What are these? I'm pretty sure I think I spelled Fineman right. These are, they look like stick figures. But what these figures are doing is giving scientists a simple, easy way to talk about particle interactions. And so it's taking a complicated situation and breaking it down to an easy way to describe it. And so when people talk about particle interactions, they usually draw these Feynman diagrams because it illustrates important things. Like you have this particle, when you have things meeting together, a place where you have three things, well, that's where you're going to do calculations. And when you do the calculations, you count those up, and you have, there's a lot of complicated math that goes into it, but this gives you all the information you need to be able to do the complicated math, except for the knowledge about the complicated math. So that's where its beauty is. So the picture on the left is showing an interaction between two protons, a positive charge and a positive charge. So the two protons come together, a virtual photon leaves one. Notice time is on the vertical axis. So you see the photon, the left proton first, and it immediately rebounded. It takes some time, so it went up before it got to the right one. When it gets to the right one, then that one rebounds and absorbs it. It's a virtual photon. What does it mean for it to be a virtual photon? It's not real is true, but it has a more in-depth meaning. Okay, it defied energy conservation for the time that it existed, and we can't measure them, which makes it really tough. Now, particle physics, a lot of it is that way. We can't measure this or that or the other thing. There have to be things we can measure, or else we're not going to have any confidence, right? Scientific method does not say, come up with an idea, the end. Right? You have to have testing. But things like these virtual particles, we can't test for them, so we have to test for other predictions that go with them. The picture on the right, what happened? Okay, they didn't actually switch, right? The proton gave off a pi plus, that's the Yukawa particle, the pion, and it converted from a proton to a neutron. And then when that pion reached the neutron, it converted from a neutron to a proton. Now, one of the very last slides of today's lecture will bring this back and show a more sophisticated Feynman diagram to show how this process occurs. But that's, these things allow us to understand what happened in a process. In studying particle physics, basically what you do is you smash things together. You take this particle and you smash it into another particle. It might be something like I'm just shooting protons into a block of lead. I'm smashing protons into whatever they hit in that lead. Or I could have protons and antiprotons that are coming head on and hit each other. But you're smashing things into it. So we call them atom smashers, right? Because that's what you're doing, smashing them together. Why?
See what happens.
Okay, to see what happens, it's really the true answer, but we want to get something that we could probably sell to grant monitors and get some money, or,
Better understand the fundamental nature of nature.
That's right. This is to try to better understand the fundamental nature of matter. If you have high energies, because energy, mass is just a form of energy. When I smash things together, I could conceivably create particles with actual mass from that energy. And the higher my energy, the bigger my wealth of particles I could create. So over at CERN, they have the Large Hadron Collider. What's a Large Hadron? Hadrons are particles that are bound together by the strong nuclear force. And so a typical hadron might be called a proton. It's a typical hadron. Neutrons, another typical hadron. Now there are more than just those. So the Large Hadron Collider is taking hadrons and colliding them together. So it's colliding things like protons and neutrons. You could go to the second level of the proton, which I think is a delta. Did you know that there's a second level of the proton? Nope. You look at the delta, you're like, but that's an up, up, down. The delta plus is an up, up, down, just like a proton's an up, up, down. You're like, why do I have the same 3 quarks making 2 different particles? And it has to do with the energy level. You have different energy levels for your combination of quarks. And when we have an atom and we excite the electrons, we just call it an excited state because the energies aren't very different. But with things like the hadrons, when you go to an excited state, the energy change like double, and so the mass like doubles, and so we call them different particles because, well, there's 2 naming conventions. Basically, they discovered this new particle, and then later they discovered it was the same thing with a higher energy, so we have the 2 naming conventions. So how do we get these high energy particles to make them go smash? You guys might remember the story of me when we were in Liberia driving home. Tried to get my dad to smash the truck into another truck because I thought it'd be the most awesome thing ever. I still do. I got my master's degree in smashing things together. To make them smash together hard, well, if you have charged particles, that's not very difficult. Because if I have, let's say, an electron, and I put an electron through a voltage difference of 1,000 volts, that electron's going to have a kinetic energy of 1,000 electron volts. Okay, so let's make it 1 billion volts. It'll have, 1 billion electron volts was more commonly known as a giga-electron volt. So we can speed them up if we have high voltages. And so that's what the idea is of the item on the left. Anybody recognize that item on the left? It didn't work when I tried to use it in class. It worked up to the minute class started, and then it stopped working. The Van de Graaff generator. The Van de Graaff generator just has that conveyor belt to give you a really high voltage. And once you have that really high voltage, you bring a particle next to it, and it repels it. You fire it away. And so the Van de Graaff generator I have, that's what it has, the little switch for beam. It's because it was actually part of a particle accelerator when it was created. You get a high voltage like 300,000 volts, and then you put a particle right next to it that's the same charge, and it repels it, fires it away. So that's an early way of getting high energy particles. Now, how many people have seen that classic movie Ghostbusters? Wow. I got 3. In Ghostbusters, they walk around with unlicensed cyclotrons on their backs. What's the cyclotron? It's another device made for accelerating particles. In their case, I think they were just using cyclotrons like they use at a hospital to increase the energy of electrons to make a high energy electron beam. In the hospital, they use those to do irradiation to try to kill tumors. They were using them to, I don't know, kill poltergeists or something. It's a funny movie, right? Well, how does it work? It's really, really simple. The first ever was made, and I swear it looks just like a little wax tin for shoe polish. I don't know about you guys. When I was a kid, every Friday I had to polish Dad's shoes. I don't do that anymore. For me either. And so we have these little tins that the wax came in, and that's what it looks like they made the first one in. What you do is you take a circle and you cut it in half. And then, now of course, you put it in a magnetic field and you connect an alternating voltage power supply. And then all you have to do is inject a charged particle here in the middle. You inject a charged particle there, and let's say this particle is an electron, so it has a negative charge. I should look at the direction, I should look at the direction things are. But if it's an electron, if you drop it in there and at that moment this side's positive and this side's negative, the electron's going to be pushed across. And it's going to gain energy equal to the voltage difference. But of course, you notice it has those little magenta circles with X's in them, a magnetic field. So because it's moving in a magnetic field, there's going to be a force that's perpendicular to its motion to make it go in a circle. And the radius of that circle depends on the speed and the strength of the magnetic field, and of course, the mass of the object and its charge. So it goes across, it's going to start doing an arc with a small radius initially because it's not going very fast. But then when it comes back, you have an alternating voltage source, and you have to have the frequency just right. So when it comes back, it's flipped sides, so now the side it's on is negative, and the other side is positive, and it gets accelerated across again. And so it's going faster, it's going to have a bigger radius, comes back. It turns out it's going to always take the same time to do a half circle because of the way the equations work out. And so you just have a fixed frequency, and it goes faster and faster and faster, gets a bigger and bigger radius until when it gets to the edge, it's going super fast. Now, there is a thing called a synchrocyclotron. This is a cyclotron because they're going around in circles. Synchro means you have to synchronize. I just said it always takes the same time to do the half circle, so why would you need to synchronize? Synchronize implies you're going to be changing the frequency to match. It's a good idea. That's good thinking. The actual answer is, my statement was only true for classical physics. When you get up to relativistic speeds, the frequency switches. And so a synchrocyclotron is a cyclotron that has to change the frequency for when they get really fast to allow you to go even higher energies. So those can make really high energies. And apparently, it doesn't take that much energy because you can just put a pack on your back and walk around and spray out your charged particles. That's a reference to the movie, in case people are not true, really. Then you have synchrotrons. Has anybody here been to Loma Linda University's proton treatment center? No? Well, they have themselves there a synchrotron. A synchrotron, in this case, it shows a nice circular path. Theirs is not a nice circular path. But a synchrotron has stages that will accelerate the particle. So you come and here it's negative and here it's positive, and the particle gets accelerated across the gaps. And then you synchronize the frequencies for changing from negative to positive. So when the particle is going through one of those blue chambers, the voltage around it is changing, so when it gets to the other end, it's the opposite. So it'll be accelerated on to the next one. And so you just have all of these things, and the frequencies have to be carefully calibrated for the beam speed. And as the beam speeds up, you change the frequencies, hence the synchronization aspect. But you can use that to create a beam. Now, if it's going in a circle, how do you make a beam go in a circle? You use magnets. They use magnets to turn the beam. And this gets really complicated because you want to keep the beam nice and tight. So tuning one of these things is a real beast because you have to adjust all the magnetic fields and have them just right. And if something goes wrong, well, there's another year of my life lost, right? So when the Large Hadron Collider came on, they had a problem with a magnet and they had to shut the whole thing down for like a year. Well, there was a lot of damage. They had to replace a big section, then they had to go through and align the beam again. So that's a synchrotron. Here is, I believe, the Tevatron at Fermilab in Batavia, Illinois, close to Chicago. It was retired when the Large Hadron Collider came online. Up until that point, the Tevatron, TeV, tera electron volts. The Tevatron was the highest energy particle smasher on Earth. Now, there had been plans, there had been construction and millions of dollars spent to create the superconducting super collider in Texas. We used to have a math professor here, Patty Anderson, her husband Scott Anderson, worked there at the superconducting super collider, giving people tours and whatnot as it was being built. But then Congress said, this is too much money on science. It was close to done, but instead of finishing it, they spent more money tearing it back down. And so millions upon millions of dollars were spent to build it, and then more millions upon millions spent to tear it back down. And so the United States lost its position as being a top place for doing particle physics research because that was the whole point of the superconducting super collider. The Large Hadron Collider is kind of, if I remember right, not going up to what the superconducting supercollider would have actually reached. But if you look here, you have two small beams, little synchrotrons that are going to accelerate a proton beam on one side, an antiproton beam on the other. And then they come in on the top ring. The top ring has the protons going one direction, the antiprotons going the other direction. It works out perfectly because they have opposite charges. Exactly the same mass, the opposite charge, the same magnetic field will bend them the same amount if they're going opposite directions. They do keep them separated in that main ring. You do not want them just colliding willy-nilly. When they're ready to do an experiment, they have some transfers to bring them down to the actual Tevatron ring, where then they bring them around, and in a special collision detector, they aim the beams so the two beams hit each other. And when a proton meets an antiproton, they go kablooey, they convert all of their energy into photons, and it's going to be mc squared plus whatever kinetic energies they had. So, gamma mc squared in the end, all converted into energy that can create more particles with big energies. It's retired, like I said, because they figured now the Large Hadron Collider's out there, we're going to be doing second-rate research. Let's not waste our time with that. The Stanford Linear Accelerator. One of the major things about this is they found lots and lots of the elements in our periodic table using this. Also, I've taken students there on field trips because, once again, it's reasonably proximal to Pacific Union College. It's a 3-kilometer-long beam. It's essentially the same idea as a synchrotron, except for it's a linear beam rather than one that's curving. So they keep the beam straight, they speed them up. It goes across, I think it goes across a fault line, goes across a freeway. It seems rather ridiculous to have this super stable beam crossing these things, but they speed up the particles to very high speeds, and then they make them go smash. So when I was there, they had what they called a beam machine. They were making particles that had the beauty quark in them. So just some of the equipment that's used. Now we get to PAM, I believe it's Paul, Dirac. Dirac is the person who, when studying particles, came up with the idea of antimatter. Now, Dirac's original idea was what we call the Dirac sea. What he did is he determined that there were some electron states that had negative energy. And negative energy states, well, that doesn't make sense. And so he came up with this idea. He said, here is 0 energy. And up here, we'll have 511 kiloelectron volts per c squared. That's a mass, right? And electrons have that mass. So here's an electron. But down below, we're going to have a symmetrical line that's at minus 5 11 kiloelectron volts per c squared. And here I'm going to have a missing electron. Basically what he says, there's this thing, he called this down here the electron sea. And he said, let's imagine that we have the entire universe is just packed with electrons. But these electrons are down here in these negative energy states. But then something happens, like a photon comes along. And the photon, if it has the energy difference equal to the separation between those two dashed lines, can take an electron from the electron C and excite it up into the free electrons that we see. I just use C two different ways, SE and SEA. And so when we talked about pair production is producing an electron and a positron. He said, well, let's just say we had electron down here, we take the electron from here, we put it up here, and we say, aha, we created an electron. But we didn't really create an electron, we just took it from down here. But down here, we're now missing an electron. And so if we had the whole universe filled with electrons, everything's good. If we're missing one, we see what's missing. In electricity, we call this a hole. So if you talk about conduction in semiconductors, you can talk about electron migration or hole migration. Here he said, okay, so it's a missing electron. And so it's kind of like the opposite of an electron. It's an anti-electron. It has a positive charge because we're missing a negative. Otherwise, it's going to be exactly the same as the electron. Now, his idea of the electron C has been abandoned, but the idea of the antiparticle, which came from this, exists. And so it turns out we now believe that for every particle, there's an antiparticle. So for the electron, there's an anti-electron, common enough that we have a name for it, a positron. For the muon, there's an anti-muon. For the up quark, there's an anti-up quark, and so on. Every particle has its antiparticle, and if the two actually meet, they can annihilate and convert all of that energy back into a photon or into something else. So Dirac came up with this idea, and that's where the 1931 and 1932 numbers I used earlier by accident with Yukawa came in. In 1931, he predicted that there should be these anti-proton or anti-electrons called positrons, and by 1932, American Carl Anderson had discovered them. I'm like halfway through my lecture and almost out of time. So the process of annihilation is what happens when a particle meets its antiparticle. Now here's something that might surprise you. You can form an electron-positron atom. An electron-positron atom is an electron and positron orbiting each other. Unlike a hydrogen atom, the nucleus doesn't exist. You have two particles with equal mass. And so you don't have one essentially orbiting the other. You have them very much doing this. And that changes the energy states. I think it cuts them in half. But you can form a balanced state with an electron and positron. But if you get to the right quantum numbers, it's possible for them to share space, right? They have different quantum numbers, it's possible to share space, and they can annihilate. So you have to be in the right state to make that stable. Otherwise, they come together, they go kablooey, and it creates two photons. Why two photons? There's a lot of conservation laws that we haven't learned. They're conservation laws that only become apparent or important in particle physics. So, I can't remember why I came to that one now. I'm sure there's a good reason. But here are things that are conserved. The first one should be no surprise. Energy is conserved. Except, of course, if it's for a small enough time. Momentum is conserved. Angular momentum, what we like to call spin, conserved. Charge, conserved. Lepton numbers. Do you remember me talking about leptons? Light particles. The leptons, we actually have three types of leptons. We have the electron, and we have its neutrino. We have the muon, and we have its neutrino. And then we have the tau particle and its neutrino. Except, you might remember I talked about the Super Kamiokande reactor where they determined that neutrinos actually have a mass. And because they have a mass, they can transform from one neutrino to another. So if you look, I did put it up, I forgot. Well, if you look at the table that's in the presentation, it doesn't call it the electron neutrino anymore. It calls it the light neutrino. And it calls it the medium neutrino and the heavy neutrino. Because those can stay, they can change. So here we have something, we define quantum numbers, the electron lepton number, the mu lepton number, and the tau lepton number, and those numbers have to be conserved unless you have a neutrino switching from one type of neutrino to another. So in an interaction, anytime you have a particle interaction, like something you can draw with the Fineman diagrams, you're going to have all three of these lepton numbers conserved. But then sometime later you could have the neutrinos shift. So that's kind of an interesting conservation situation. During the interactions it has to be conserved, later it doesn't have to. But it's only with neutrinos. Baryon numbers. What's a baryon? Baryons mean heavy particles. Baryons are a subclass of the hadrons. Hadrons were the things that used the strong force. Baryons are the heavier ones. Mesons are the lighter ones that use the strong force. So baryon number. Simple way to remember your baryon numbers. A proton has a baryon number of 1. A neutron has a baryon number of 1. Electrons are not baryons, hence they have a baryon number of 0. Other particles with baryon numbers are going to be larger, and if you're using larger particles, you'll just have to look it up. If a proton has a baryon number of 1, what would an antiproton have? -1, because the quantum numbers flip. Now, those are our basic conserved properties. I'm going to get to 2 slides, and then we'll quit. This slide here, I'm not sure if this is the same one. I think it's a cleaned up version of the one that the 4 young ladies showed in their presentation yesterday. How do we know anything about these particles? It comes from observations such as this. This here is actually the observation that led to the identification of the omega minus particle. And they have here a kaon minus that decayed, that dash line for the kaon 0, K0. It's dashed because you don't see it. So on the actual picture, you don't see that. Likewise, you don't see this C0. You don't see the photon. You don't see the lambda 0. You don't see the photon there. And so when you look at these, it gets really complicated at trying to figure them out. Well, it's something you have to do for experience. But that's the point of the cloud chamber, being able to do these things to identify particles. When people were studying particles, they found, okay, there are very few things that are stable. The electron's stable, the proton is stable, the photon is stable. But even the neutron is not stable. How many people knew neutrons were not stable? I only see one hand. Neutrons have an average lifetime of 882 seconds. That's if you have a neutron just by itself, not in the nucleus, in 882 seconds on average it will decay, undergoing a beta decay. So neutrons are not stable. The lifetimes tell us about the forces that things are breaking down by. So things with extremely short lifetimes have very strong forces. So something that is very unstable and decays really quickly is decaying via the strong nuclear force. Things with a slightly longer lifetime, electromagnetic because it was the next strongest, longer still the weak. But when scientists were studying these decays, they found some decays never occur that should occur. And other decays that should occur quickly occurred slowly. And they said, this is really, really strange behavior. And that led them to the names of our quarks. The quarks, they started by identifying what they called isospin. It behaved like spin, but it wasn't angular momentum. So they call it isospin, kind of like the same as spin. And they started categorizing things by isospin. And then Murray Gell-Mann, there was another dude that did the same work somewhere else. I don't know his name. He proposed that there would be 4 fundamental particles called he called them aces. Murray Gell-Mann called them quarks. And he got the name from Finnegan's Wake, where it says, and 4 quarks for Buster Mark, or something like that. And so he called these the quarks. The first 2 they just called up and down, because they thought that it was 2 charges like we have 2 electric charges. But this strange behavior actually was the result of a 3rd quark. So that 3rd quark, when they discovered there was a 3rd quark, initially they had sideways, somewhere between up and down, sideways. But then, because the strange behavior was described because of this other quark, they called it the strange quark. And it's convenient that it's still S. But their theory at that point said there should be 4. And so they said the 4th one must lead a charmed existence because we can't find it. And so they named it charm. And then they discovered there must be 2 more for matching the number of leptons. They found the tau. And so they named the last 2 top and bottom. And that's where scientists said, top and bottom, that's way too boring. So they have alternate names of truth and beauty. So we have 6 quarks, up, down, strange, charm, truth, and beauty. Everything that we're familiar with is in the first category, the ups and downs. Protons are up, up, down. A neutron is an up, down, down. I'm going to have to stop now because I've gone 5 minutes over. But what they found was strangeness is partially conserved. Strangeness is conserved if something decays via the strong nuclear force. It's not conserved if it decays via the weak nuclear force. That's the ultimate upshot here. Have yourselves a sweet day. I'll see you on Friday when we will review.